This is a Math 3 summary video for the lesson titled, Is This the End? This is a Solidify Understanding task. The purpose of this lesson is for students to relate the degree of a polynomial to the polynomial's rate of change and end behavior. So there are several main points that this task makes. One of them is that the degree of the polynomial is the highest exponent and determines the end behavior. So let's take a look at a few functions. So here's a linear function, so the degree is 1. So I'm just going to change the degree, and we can take a look at the end behavior. So notice these ends are pointed up. This one's going up, that one's going down. That's similar to the quadratic. Another up and down. It's also similar to the quadratic. End behavior going up and here going down. So I don't know if you've noticed this pattern, but if we have a polynomial with a degree of 1, 3, 5, 7, 9, 11, or really any odd number, then the end behavior is the same. On the left end, the function is headed towards negative infinity, and on the right end, the function is headed towards positive infinity. So for any of these polynomials that have an odd degree, we have the same end behavior. If we did more to the function, added a few more terms to it, it doesn't change the end behavior here. Here's another function, and you can see it does not change the end behavior. End behavior where one end goes down and the other end goes up, we have these polynomials that have an odd degree. Other examples to add to this would be f of x equals x to the 7th plus 2x to the 6th plus 5. As long as the degree of the polynomial, in other words, the highest exponent, is an odd number, you'll have the same end behavior. Now, we also saw when we were first exploring some of end behavior that had both ends going up. So a few examples of this type of end behavior, where as x is approaching negative infinity, f of x is approaching positive infinity, that's that end. And as x approaches positive infinity, f of x approaches positive infinity, that's that end. And then we can add one other example. Let's say f of x equals, I'll do x to really any even number, I'll put 20, plus 3x to the 2nd power plus x minus 4. As long as the largest exponent is even, then it'll have this same end behavior. Okay, so we didn't see any as we were first exploring that had end behavior that looked like this, where the left end was going up and the right end was going down, or both were going down. To have both ends going down, you should remember from your study of quadratics that you just have to reflect the polynomial over the x-axis. So I'll make that negative. And then sure enough, any other even exponent, no matter what I add to it, it's still going to have the same end behavior. So I have my negatives here to make sure I'm reflecting, and then I'll add one other example. I just need to make sure that my lead coefficient is negative, like negative 2x, and then I have to have an even number here. So I'll do 8. And then plus 2x to the 7th. As long as the largest exponent is an even number and my lead coefficient is negative, then I'll have this end behavior. And returning back to Desmos to get this other end behavior where the left end is going up and the right end is going down, I'm just going to put a negative on my odd exponents just to check these. 1, 3, the 5th power, to the 7th power, to the 9th power, to the 21st power, and I'll maintain the same end behavior no matter what else I add, as long as the largest exponent is an odd number and my lead coefficient is negative. So here are a few examples, and then I'll add one more. F of x equals negative 2x to the 7th power plus 50. The other thing we need to look at is what happens to the rate, the growth rate, when you increase the degree of the polynomial. So let's return to Desmos and enter a few other functions to see if we can figure out what happens to the growth rate as you increase the degree of the polynomial. I'm going to make this so I can look a little bit closer at the first quadrant. And you can see from this graph, this is f of x, and then g of x equals x squared, h of x equals x cubed, j of x equals x to the 4th, and k of x equals x to the 5th. So as you increase the degree of the polynomial, the growth rate also increases. Let's also compare this to an exponential function to compare the growth rate. Right here, it looks like the polynomials are growing faster than the exponential, but if I zoom out, eventually, the exponential function will grow faster than the polynomial functions. So higher degree polynomials grow at faster rates. And here's f of x equals x, and then x squared, x cubed, x to the 4th, and x to the 5th. So you can see that the steeper graphs have the faster rate. So we are talking about here where x is greater than 1, since the rate is a little different with the smaller values of x. But over time, the higher polynomial function will grow at a faster rate than a lower degree polynomial function. So another way we can classify functions is by classifying them as even, odd, or neither even nor odd. So here are some examples of even functions, odd functions, and then functions that are neither even nor odd. Here you can see we have m of x equals x squared and k of x equals negative 3x to the 4th plus 2. Even functions are symmetric about the y-axis. Functions with an even degree, so our polynomials with an even degree that have not been horizontally shifted, are even functions. Here you can see a even degreed polynomial, so a quadratic. It does have the same end behavior as this even function, but it is not considered even because it is not symmetric about the y-axis. In other words, the axis of symmetry is not the y-axis, is not x equals 0. So these are two examples of odd functions. I have j of x equals negative x and h of x equals 2x cubed. So you may have noticed that these have an odd degree. So this one, its degree is 1, and this one's degree is 3. Odd functions have 180 degree rotational symmetry about the origin. So functions with an odd degree that have not been horizontally or vertically shifted. When we talk about rotational symmetry, what that means is I can rotate this graph 180 degrees, where the center of rotation is the origin, and the graph looks exactly the same. This one too, I can rotate it 180 degrees, and the graph looks exactly the same. So neither even nor odd would mean it does not have 180 degree rotational symmetry about the origin and is not symmetric about the y-axis. So this other example of a function that's neither even nor odd does have the same end behavior as this cubic function right here, and it is a cubic function. However, it does not have 180 degree rotational symmetry. That looks different than this. So it is neither even nor odd. Alright, now that is it for this video. Thank you for watching.